And most people think it's just a sensor. We'll stick it out there, we'll put it connected to the internet, no problem at all, we'll get those readings. What I'm really looking to provide today is more of an insight into how we made that sensor. What lessons have we learned through over 7 years in the IoT sensor market in terms of the physical design, test, validation, and use cases of IoT sensors. So I'm Jonathan Kaye. I look after product management for Ezurio. Ezurio was formerly led connectivity. If you've been to any of these things conferences before, the big blue gateways and blue sensors, they're ours. We also are a designer, developer, manufacturer of wireless modules, particularly Bluetooth, Wi-Fi, LoRaWAN, UWB. We make our own antennas. We're actually a test house of our own. And in addition to that, we are also a manufacturer of IoT devices off the back of those modules we just talked about. And that's what we're really going to focus on today. So trying to bring this into the reality of a market or an application, this talk will focus purely on QSR. QSR stands for the quick serve restaurants, or to me, fast food restaurants. So we're going to talk about an environment where there is constant cleaning, there is grease, there is gunk, there is a lot of metal. All kitchens, all walk-in freezers, all fridges, it's just a big metal box. How can you propagate the RF out of that environment robustly and reliably? These are chains that are all over the world, in all countries. They need to have a relatively global footprint for the IoT sensor and device that goes into them. So, it's just a sensor, easy peasy. I'm sure everyone can do it. You take a temperature sensor IC, you add wireless, done and dusted. Really, the challenges come from the environment, and we talked about quick serve restaurants. It's not the prettiest, it's not the nicest, and again, heavy use of metal in the enclosures. Performance, the RF must push and penetrate out of that metal environment. Again, why LoRaWAN as a solution is very good for the environment. The users are people that flip burgers, cook fries, and serve food. These people are not IoT technicians, experts, or engineers. They have to be able to use them without thinking about where's the complex 19-step stage to be able to take the battery out and reset this device. The installation must be simple and easy. Again, I can't have a set of engineers going out installing these things in the optimum location. They zip tie them to the racks or they stick them on with magnets. That's it. Done and dusted. Maintenance, they must last for years. Full stop. They must not break. They must just keep working. They live in a freezer. Size, cost, and globality. Size, nobody wants to see the IoT devices in these environments. They need to not be hidden as such, just not be very obvious. Why? Because then users start playing with them, they start messing with them, they start breaking them. Cost, they've got to be inexpensive. This is temperature we're talking about. But again, if your freezer goes out of temperature and that food is wasted and the spoilage from that freezer, that's a lot of money in its own right. And then globality again. McDonald's, KFC, Five Guys, they are everywhere across the globe. They need a solution that is as relatively global as they can get. The three-legged stool. So to me, this is relatively simple. I tested this against some of my US colleagues. They had no clue what a three-legged stool was. So it's literally a stool that has 3 legs. They all have to be the same height to be balanced. And for this, we were particularly focusing on the product size. It couldn't be too big. The product cost, it can't be too expensive, obviously. Ease of use and maintenance for those environment and the users that we have. And in this kind of mix becomes your battery life, the sensor, the RF performance, the enclosures, and everything else that comes around it. So how do we make a balanced solution? And we'll get to some of those trade-offs as we talk through each of the different aspects of the design. So first thing we always try and do as an organization, as an engineering company, is how do we reduce technical debt, both in the hardware and in the software? How do we reduce technical debt to increase TTM, time to market? So in our sensor, we reuse our own modules. So I said at the start, we're a designer and developer of wireless modules. We have been for a couple of decades now. So inside this product is our RM126x for LoRaWAN using Semtex 126162. And then over on the right, we're using a Bluetooth MCU from Silicon Labs, the EFR32BG24. Why are we using those components? They are known, tested RF. They are fully certified. They are reliable solutions that we have used for several years and will continue to do so. It provides reliability of RF and performance for customers. And for us, everything that we put into these modules, we benefit and reap the benefit of that into the finished package device that we produce. Again, lowering our technical debt, improving reliability. On the software side, over the last kind of 4 or 5 years, we developed something called Canvas Software Suite. This is layering on MicroPython or Python-based application scripting on top of the SDKs and stacks that we get from our vendors. So why is this a benefit for us and our customers? So across all of our MCU-based devices, we abstract the RTOS, we abstract the SDKs, we abstract the wireless elements, and provide simply the application level development for the customers to program in Python. You do not need to be a LoRa expert, a Bluetooth expert, or anything else in between. You're going to write your application in Python, load it over the air via Bluetooth, load it through the devices themselves, and abstract you away from Zephyr RTOS, from FreeRTOS, from Simplicity Studio, from the NRF Connect SDK. You just focus on the application environment and not on the underlying stacks and complexity underneath. Again, for us, we've tested this across all of our products for many, many years. Robust, reliable, reuse, recycle, lower our technical debt of development. Putting that into practice, so from our original device, this was the first LoRa sensor we took to market, our RS1XX. Complete monolithic software architecture, all written in C over many, many years, adding regions, adding features, adding different requirements for customers. We had individual firmware loads for different regions. Our operation teams hated us. We had to have SKU after SKU after SKU. It was very difficult to maintain and became very complex. For us, a high level of technical debt. And for customers, there is so much change and complexity, errors can creep in. For the new software stack with the new environments and Canvas, one application layer, one set of protocol, one scripting, we have full codec generation automatically, much simpler for customization, lowers our technical debt, improves reliability for the customer. If you look then completely changing gears into the devices themselves. So in reality, you want the longest possible battery life. What do? The biggest clunking battery you can stick in there possible, longest battery life. But that has a massive impact on RF performance. It has a massive impact on the thermal mass of the device. If most of your battery is taken up here, where is your antenna going to go with the clearances around it that you need? So always trade off. Back to that three-legged stool. If we just focused on longest battery life, that stool would be unbalanced and it wouldn't be what we're looking for. So we ended up going with the CR123A as our ultimate solution. But in batteries, you think fairly simple. You know, what size, what cost, what regions do you want to support, what's the ESR of the device, what is the voltage levels. We found one thing through all of the testing and validation: never believe a manufacturer's data sheet, test it for yourself. Test it at temperature ranges. Test it across the different spectrum that you want your device to operate. Your whole product can't fail because of a poor battery that's inside of it. Not all batteries are the same. Do not treat them equally. And again, look at the battery as a system-level solution, not as a component within it, because the battery is going to have knock-on effects throughout the rest of your design. Wireless design, the antenna performance. This is a walk-in freezer. This is where the bulk of our products are installed. It's a big metal box. Not great for an antenna, and we're looking to have a single PCB that can support 800 and 900 megahertz. Quite a large range, quite a big set of frequencies to be able to support. Terrible RF environment, and they're going to be deployed attached to metal. Again, not very good for the antenna and the RF propagation. Thermal mass becomes a significant concern in this kind of environment. What we ended up doing was designing both the antenna and the PCB and the layout of the device, where we actually took advantage of the metal that we were actually being installed on to use the reflections from the metal to get better directivity of the antenna, as you can see from this test here. What you can do, though, is you can design for cheap. You can design for an antenna like this Helix here next to a massive battery. Yep, very cheap. Terrible RF performance. Again, back to your three-legged stool. What is it that you want from your product? How do you make a balanced, robust product for the market? Temperature delta and response times. So again, temperature just records the temperature in a device, but try and do that for a spec like EN12830. EN12830 is for cold chain in the transportation industry for perishable food items. The requirement is that within 20 minutes, a 20°C change of temperature is up to 90% in your device. Basically, how quickly can it react to that change in temperature? And that has to be tested by a third party and certified. We tested everything we possibly could. Fairly simple graph here with fail and pass on each side. Each different tooling that we did, each different design, each different enclosure, each different iteration of the antenna, the different battery types, the thermal mass, all had an impact on this delta and the response times that we've got. You've got to look at, again, everything in totality, nothing in isolation. So it's all about the entirety of the enclosures, the PCB, the antenna, not just about the temperature and sensor IC itself. We made this really simple. It's quite a simple block diagram showing the evolution of our design, and we'll talk about the enclosure design on the next slide. Here's your 20-minute line of original product, and then down through the different iterations of the product as we designed it to meet that EN12830. And here's one of the examples of what we did. So the original design, this Rev1, barely passed. We provided more thermal isolation for the temperature sensor IC by cutting away the PCB that's around it so that you can get better kind of change in the temperature range. So again, looking at all the things that we can do at every single aspect of the device to provide for a robust, reliable end solution that is more than just something that records temperature. The enclosure evolution, this was our development cycle through time. Engineering got really friendly with some of them. This was Sideshow Bob, this is Uvula, this is Dingus, as they tested different characteristics of enclosure, the antenna and the insides. So showing how the design evolved over time. This is Uvula. We thought we'd cracked it. We were done and dusted. This was the end of all of our work here. This kind of ingress you get around here with the temperature sensor IC, excellent for everything. The welds held, everything held. Unfortunately, they forgot about our environment. That ingress gets full of ketchup, gets filled with gunk. Our customers, it would not work for them. So again, a 99% perfect design that failed at the end of it because it didn't match the environment and what our users required. RF approvals. Anyone here in the LoRaWAN knows this is quite complicated. Lots of regional requirements, 10 different bands that we're supporting. We have Bluetooth and LoRaWAN, so we have to have the 10x rule for North America. For emissions, that's up to 25 gigahertz of testing. Expensive, time-consuming, problematic. Reusing our own modules helps with that. A known reliable thing with certification helps us speed through that process. And a single PCB, very much loved by our operations team to simplify their supply chain. Then, Red Cyber, EN18031. Protect your network assets. It's a 120-page spec. It's 500 plus questions that we had to answer. We went above and beyond in that to provide a full notified body certificate. We provided hardware bombs, software bombs, drawings, SCRBs, schematics. Does your product have it? From August, last month, you should. You must, in fact. Really rolling all of that up. Sensors on the surface look very, very simple. They need cross-collaboration between all aspects of your development team. Every single design choice is a trade-off. You can't think of them in isolation. Hardware, software, enclosures, IDME, certifications, all need to be looked at in the round. Cross-disciplinary collaboration for us was key, getting everybody on the same page to match the requirements. And I think this is always an interesting one. Things are generally cheap for a reason. There's always a reason why they're cheap. It's either in the materials, it's in reliability, it's in performance, it's in test, or it's in validation. You have to cut the cost somewhere. Ask your suppliers, why is it that price, and have they done all of this testing and validation to ensure you have more than just a sensor, you have a robust, reliable solution that your company will back with your own name on it. And that is it. Thank you very much.